Here's the graph y equals 2 to the x. And the question I want to ask is, what is the gradient of the tangent at that point, the green point, where it crosses the y-axis? That's the point 0, 1. Well, we'll proceed as we normally do for finding gradients of curves. And we'll draw a line through 2 points, one of which is the point we're interested in. And we can work out the gradient of that line pretty easily because the y step is 2 to the h minus 1 and the x step is h. And let's see what happens when h gets smaller and smaller. The blue line gets closer and closer to the tangent. Until it's very close to the tangent. H is just 0.0001. When we hit the tangent, it can't calculate it anymore because then we've just got 0 divided by 0. There's only 1 point on the curve. But what we can see is that it's getting closer and closer to a particular number. And that number that it's getting closer to, at least to 5 decimal places, is 0.69315. So less than 1. What would happen if instead of y equals 2 to the x we had y equals 3 to the x? Then we'd have a bigger gradient. As h gets closer and closer to 0, the gradient gets closer and closer to 1.09861 to 5 decimal places. So a bit bigger than 1. So for y equals 2 to the x, the gradient of the tangent is a bit less than 1. And when y equals 3 to the x, it's a bit more than 1. So there ought to be a graph using a number somewhere between 2 and 3 where the gradient is exactly 1. So let's see if we can find that. Okay, the gradient's going up. Y equals 2.5 to the x, we're getting pretty close to 1. Oh, a bit too far. Let's try going down a bit. And we've gone back too far the other way. So somewhere around 2.718 is a number that makes that gradient equal to 1. And in fact, to 5 decimal places, that number is 2.71828. In fact, that decimal never ends, but we've got a special name for that number, and that number is e. So the limit of e to the h minus 1 over h as h goes closer and closer to 0 is 1. That's going to be our working definition of e. Not an easy definition to use to calculate e because you have to do a lot of trial and improvement. But that definition does have some consequences because for small values of h, that's approximately true. Which means that's approximately true. And the smaller h gets, the better that approximation is. So e is actually the limit of that as h tends to 0. And now we can calculate e just by working out 1 plus h to the power of 1 over h for smaller and smaller values of h. Or we could make 1 over h equal to n, so n is getting bigger and bigger now. H is 1 over n, 1 over h is equal to n, and when h is going to 0, n is going to infinity. And now we can just calculate that for bigger and bigger values of n and get e to as many decimal places as we want. So there's e to 5 decimal places. There's e correct to 15 decimal places. And we can look at e yet another way and find yet another way to calculate it. Remember from the binomial theorem that 1 plus 1 over n to the power of n is 1 plus n times 1 over n plus n times n minus 1 over 2 factorial times 1 over n squared, and so on and so on. And as n gets bigger and bigger, n times n minus 1 over n squared gets closer and closer to 1. And the same for the next term, n minus 1, n minus 2 over n cubed gets closer and closer to 1. And that's the same for every term. So as n gets bigger and bigger and bigger, we're getting closer and closer to something with just the factorial terms left. So e is the limit of that thing as n tends to infinity, the limit of that. So e is 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and so on and so on. And that series gets close to e really pretty quickly. You only need about 20 terms to get e correct to 15 decimal places. So now we know what the number e is, and we know what the curve y equals e to the x looks like. But what's the gradient of the curve at any other point? For example, this point here. Let's draw a line, as usual. There's my point with x-coordinate x, and another point with x-coordinate x plus h, and we can easily see what the gradient of that red line is, because the y-step is e to the x plus h minus e to the x, and the x-step is just h. But we can factorize, take e to the x outside the fraction, and we get that. And of course, that fraction, e to the h minus 1 over h, is something that we recognize. So dy by dx is the limit of that thing as h tends to 0. Remember that as h tends to 0, the red becomes the tangent gradually. There it is. But the e to the x is not affected by h, so we can take it outside the whole limit business. And of course, that limit is equal to 1. We know that from our definition of e. So dy by dx is just e to the x. So here's e, the limit. Now I've used m instead of n. You'll see why in a moment. So e to the power of x is just that thing to the power of x. Now I'm going to put n is equal to xm. So 1 over m is now x over n, and we get e to the x is that limit there. And that's a very important formula for e to the x. Let's check that when we differentiate we still get e to the x. So using this definition, then the differential of e to the x is the differential of that limit, which I claim is the same as the limit of the differential. And I can differentiate the brackets quite easily. Bring down the power, reduce the power by 1, and times by the differential of the bracket. And the n's just cancel. Now, 1 plus x over n to the power of n minus 1, that's 1 plus x over n to the power of n, divided by 1 plus x over n. But as n gets closer and closer to infinity, that thing on the bottom of the fraction just gets closer and closer to 1. So that really is the same as e to the x. Earlier we figured out what e was as a power series. And we can do the same to find e to the power of x. So notice that 1 plus x over n to the power of n using the binomial theorem is that thing there. And e to the x is the limit of that as n tends to infinity, which is the limit of that, and just as before, we're just left with the factorials in those fractions. All the n terms cancel. So e to the x is that series there. Let's look at some graphs involving e to the x. For example, y equals e to the x over x. And let's see if we can account for some of the features that we notice on the graph. Obviously, when x is positive, y is going to be positive, and when x is negative, y is going to be negative. But what about the turning point? Let's differentiate. We can use the quotient rule, or we can use the product rule. Let's turn it into x to the minus 1 times e to the x and use the product rule. Okay, we can take x to the minus 2 e to the x outside the brackets and factorize like that. And now we can see easily that there's a turning point when x is equal to 1. So that accounts for the turning point at 1e. What about e to the x over x squared? Turning point is now when x equals 2. But there's also another difference, which is that when x is less than 0, y is now positive, and dy by dx is also positive. And just by looking at those formulas, we can see pretty easily why that is. So when x is greater than or equal to 2, the gradient is greater than or equal to 0. When it's between 0 and 2, it's less than 0 for obvious reasons. And when it's less than 0, the gradient is positive. That's all pretty much the same as e to the x over x, except for the fact that when x is less than 0, the gradient is now negative and y is negative. So e to the x over x, e to the x over x squared, e to the x over x cubed, now the turning point is when x is equal to 3, e to the x over x to the 4, over x to the 5, over x to the 6, and so on and so on. So we can pretty easily account for all the features except for one, and that is that y gets bigger and bigger as x gets bigger and bigger, but y gets bigger without any limit. Why is it that y should not tend to a limit as x tends to infinity? Well, let's see. Remember, we've got this power series for e to the x, and that means that e to the x has got to be bigger than any single term when x is positive. And that means that e to the x over x to the n has to be bigger than 1 over x to the n times any single term. But if we choose m is equal to n plus 1, then we've got that. But that simplifies, and that obviously tends to infinity as x tends to infinity. So e to the x over x to the n tends to infinity for any positive integer n. That's to say, e to the x grows faster than x to the n for any integer n greater or equal to 1. What about graphs of the type x to the n over e to the x? Well, let's start with x over e to the x. We can see straight away here for x over e to the x that y is going to be positive when x is positive and negative when x is negative. What about a turning point? Let's differentiate, and we can see there's a turning point when x equals 1. There it is. When x is bigger than 1, then the gradient is negative. When x is between 0 and 1, the gradient is positive. And when x is less than 0, the gradient is greater than 0. And we can also see that it obviously goes through the point 0, 0. What about for x squared over e to the x? The only difference now really is that when x is less than 0, the gradient is less than 0, because x times 2 minus x is going to be less than 0. Of course, dy by dx will be equal to 0 when x is 0, so long as n is 2 or more. So we've also got a turning point when x is equal to 0. And now we've really accounted for all of the features of the graph, except for when x gets very, very, very big and positive, that the graph tends to 0, that y tends to 0. But that's easy to see now, because we know now that e to the x grows faster than x to the n for any integer n is greater than or equal to 1. So x to the n over e to the x must tend to 0 as x tends to infinity.